so I did my capstone project on a replacement open protocol for getting rid of passwords, essentially. I mean, we all know how terrible it is to have to deal with passwords on so many different platforms, having to have secure passwords that change from site to site, that it's essentially a secret key that we have to share with someone else. And every time we share a secret with a different third party, the likelihood of losing that secret increases with every single person. So the idea, the impetus behind this project is to essentially create a way to prove that you are who you say you are without actually having to share real secrets with another party. And really the way that this, the fundamental technology that this protocol relies on is the public and private key cryptography. You guys know, are you guys familiar with public-private key, how that works? So basically what this is you have, in most systems you have basically your symmetric key. Basically, secret goes in one side, comes out the other side, looking a little bit different. And as you take this key, you pass your information from one side to the next. It changes predictably, but in order to get back, you have to use the exact same key. The way that public-private key cryptography works is that you have your private key. And your public key. So the way that this works is that you take your information, put it into this key. It comes out this side as a jarbled mess. And then passes through once more, and then comes out the other side as high. And that's the basic way that this works. So if I encrypt this word high with my private key, the only thing that can decrypt it is my public key, and that's what's called signing. If you go the other way, if you take your public key and someone else wants to send you a message, anybody who has a public key can then use that public key to encrypt, come back, and then I'm the only one who can decrypt it. So this is the basic idea behind it. So the way that this protocol works is that you create a private key and a public key. You have your private key, which is deterministically created on your end from both a master ID and the site's domain hashed together. And that creates a private key, which you can use to create a public key. You give this public key to any other website. They attach a username to that. And what they do is they say, okay, so I have this username here. And then I have this private key. Just a binary chunk of data. And what I need you to do to prove that you are the person who controls this username here is we're going to give you a number. Doesn't matter what it is, it's just a randomly generated number. And the website then gives you this number and says, okay, so the only way that you can now prove to us that this is your number is if you give us a piece of data that comes back and we can decrypt with this. So on your side, you take your master key, and then out comes your private key. And then you take the number, and then out comes a bunch of gibberish. 2, 4, 3, 1, whatever. And then the website says, okay, puts that through your public key. Out comes 1, 2, 3, 4. All right, cool. So no one else can do that. No one else has a private key that you can use to encrypt this nonce here. And at the end of the decryption with your public key, get out what they sent you. So now you're who you say you are to them. But nowhere in this has any information actually traveled from you to the server that you don't care about anybody else having. So that's the sort of 5,000-foot overview of how the basic plumbing of this system works. And the reason why I got into this was because this is developed by a gentleman named Steve Gibson. He's got a podcast called Security Now, where he sort of explained the basics of this. And this is all known cryptography. And the method to putting it all together is novel, but nothing about this is actually fundamentally new. It's just an interesting application of known technology. But what this really allows us to do on the internet is not only give the website a very simple way of proving users are who they say they are, sort of across time, without having leaking out. But also, on our end, there's only one password we need to have here, and that's the password that controls this master ID. So there's just one password. For the entire universe of every single website, every time you need to send someone private, you need to create a login anywhere, is generated from this master key. So this is the only place where you need to have a password. That's one password for everything. This does tie in a little bit to a device, but the way that the protocol is set up, it's actually fairly easy to export this information into another device, and then, again, only your password is going to decrypt this. So, and then over here, because this is a public key, the website that you're authenticating against, they can lose this. This is information that they can actually just share with the entire internet, and you don't care about that. Because the only place you're ever going to actually use this is when you're trying to say, oh yeah, I'm Almond logging into this website. It's the only time. Nothing about having this information gives you anything about having this information. So that's the fundamental fascination that I had, is that it's very, very simple. So what I did for my project was I created this very simplistic plumbing, a very, very simple version of this. The only thing it does, it takes in as a string the domain name, the nonce, and gives you out as another string this binary chunk of data. It doesn't actually do any of the actual cross-internet communication. This is a command line application that essentially would serve as sort of a headless backend to any other program you might want. And really, because this is all, and it's all known cryptography, very actually quite simple. I'd be willing to bet that basically anybody here could do the same project. So questions or?
Questions. Yeah. How does this either work with, work against, or not even mix at all with like two-step verification and stuff like that?
Well, this actually has the capability of sitting alongside any other authentication system. And the really neat thing about this is that this can actually be an out-of-band authentication, or it can be an in-band authentication. You can use it with a one-time password-generating fob. You can use it with traditional passwords. This doesn't. The use of a system like this doesn't preclude any other authentication system. This is just one thing that you can use you can use this only, or you can use this in parallel or in conjunction with any other system you'd like. I saw a hand. Yeah.
Yeah, I was wondering so the number that you need to generate, does a user have to enter that? Is that cached on the user's machine?
So which number? This one here?
That number, yeah.
This number is actually sent from the server.
Okay.
So the server just grabs a random number, whatever it is, and sends it to you. You encrypt that number with your private key, send it back, and if the server decrypts it with your public key, and it comes back the same thing that they sent, then they know that that's you who they're talking to.
I understand. So it's a new number every time.
Right.
If it's generating these new numbers every time, is that going to add a lot of overhead?
For this one?
Yeah, for switching it back and forth on the server.
Well, the number is discarded after use. So the only thing that you have to have is sort of a pool of entropy being continuously refreshed on the server side. Okay.
Thank you.
All right. Thank you.
All right. So our next talk is by Scott Walker, who has worked with Dr. Dubois. Scott.
Hello guys, so I'm going to talk about how I hacked a Linux system which was riddled with security flaws. So, for those of you who aren't familiar with the stack, it's a pretty simple concept. It's a space in memory where, say you need more data, so every time you throw something on, put it on the stack and it builds up, kind of like a stack of papers, and you keep this stack pointer which keeps track, okay, this is where my top is. And as your stack grows larger, your addresses get smaller. So how a buffer overflow works is, say we have some small buffer somewhere, it's on our server, and then we're going to copy a string into it. But what if you use a copy function that doesn't ask about the sizes, it just throws that data in there? So this is going to be the result on your stack. And below here, your base pointer, is where the return address to the previous function is. So it's going to try to return to B. Your computer's not going to let you do that. You're going to get a seg fault. So let's talk about shellcode. This is just a group of instructions that you're going to try to inject into a vulnerable program. It could be a virus, could be an exploit. There's tons of different ways you can do this. So the main way that people have done this in the past is by using the same stack buffer overflow technique that we know. And when they overwrite that return address, they try to have it point back to their shellcode. So this is kind of what that looks like. No, this isn't actual shellcode. This is just some arbitrary instructions I threw on here. But the important thing is right here below RBP, where your return address is, you've stored the address for your shellcode. So unfortunately, the people who make compilers also know about these tricks, and they don't want hackers to be able to do this. So they put this thing on the stack called a canary, and it goes right above that return address. And before the function pops out of that stack frame, the program's going to check to say, okay, is this canary valid? Uh-oh, it's not. So that means someone smashed the stack. And that smashing the stack is just a term used for when that return address is overwritten. So this is what that looks like. You have your buffer, a bunch of data in it, and right here, before your buffer, or after your buffer, but before the return address is where you store that canary value. So operating systems also have some security features. One feature is typically you have sections of your program where your functions are, and then you'll have the heap and the stack. And there's no real reason why anybody needs to be executing things off the stack. So operating systems typically don't let you do that. However, a programmer can request memory pages that are executable. So if you don't know what you're doing, you can create lots of security flaws very easily by doing this. There's also this feature called ASLR, which just means that it stands for Address Space Layout Randomization. All that means is we're going to randomize all of the addresses for the heap and stack and even sections for system calls so that we can't use some predictable address to execute our shellcode every time. So with all these security features, you're probably wondering, why the heck do I need to worry about security? Should the operating system just take care of this for me? And this isn't actually true because, like I said, if the programmer really doesn't know what they're doing and they're just blindly writing code without thinking about those things, you can very easily create a program that the hacker will be able to exploit even if all these security features are in place. And in addition, there's lots of times when administrators may turn these features off. Maybe they don't know what they do, and they're like, oh, well, why do I need this thing? Or there's some situations where maybe they have to turn it off to test something, and then they'll forget to turn it back on. So with that being said, now I will demonstrate an actual stack buffer overflow on a vulnerable server. So the trick is here. I wrote a very simple socket listening server. All it does is takes data over the network, and my shellcode tells the program to call this Linux utility some of you may have used called wget. And there's this thing in Linux called a shadow file which stores all your passwords, including passwords for logon. So what I do is I tell wget, let's just overwrite this file and pull some shadow file that I threw up on the internet with a new password for root in it. That way, I can remotely log into root once this successfully executes. So let's execute the server. So now over here, on the window on the left-hand side, what I have is a program that will send this shellcode. And this is just to make my life easier because there's some techniques I use in it. Some of you may have heard of a no-op sled, which just means it's just a bunch of techniques that I use to make it so that my shellcode is more likely to execute. So let's run this over here. Oops. Okay, so as you can see, this output says /etc shadow saved. So that means my shellcode has successfully executed on this program, on my server. So if I come over to my local machine, now I should be able to SSH in as root with this new password, which I changed to 5678. And note, before the root password was 1234. So, and there it goes. I'm now logged in as root. So, for this demonstration, I actually did this with ASLR turned off, but I was working on a technique that would actually still execute my shellcode even with all the security features turned off. I didn't bother demonstrating it here because I'm still not 100% successful. I was getting it about 25% of the time at best. And I used a similar technique. More or less what I did was I had, say your server passes in your buffer by reference. So then what you can do is overwrite the previous stack frame, put your no-op sled above in that stack frame, and then below that return address you throw your shellcode. So that way, even though there's canaries and ASLR, you don't give it an address, you just let it jump back to where it wants to go, and you've placed your shellcode there. So that is my presentation. Does anyone have any questions?
Seawolf safe.
Yes, Seawolf should be safe. As far as I know, Roger definitely has ASLR on. By default, canaries are enabled, but that's another thing is that this is the worst case scenario for security. This potential user has run their server as root. They've enabled SSH in as root. ASLR is off. Pretty much the worst possible case you can have. There is technically no safe system. People are always discovering these new techniques to get in. A lot of you have probably heard of Heartbleed, So that's the key thing is stay on top of security updates. Don't use outdated software. People running Windows 2000 doesn't really have a lot of these security features, so definitely don't use outdated software. Yes?
So why is the canary the first, or pointed to by the base pointer, not below it?
So the canary, it's a little tricky. there's actually more than one canary on the stack. I just showed that one because it's the easiest to understand why it's there. So the main reason you do that, the compiler is going to optimize your code in certain ways, and then it also does some tricky things without letting you know. So say you have a bunch of variables in your stack, parameters, things that you're passing in. Actually, I should probably just draw this up over here. Make this a lot more clear. So let's say I have some stack frame, and up here you're going to have your parameters for the function. And then let's say I have some local variables to this function. Down here we'll have my return address. And there's my canary. So what the compiler does sneakily without telling you is that it's always going to put any character buffer you have right here, below your locals and above the canary. And it does this so that this canary is always going to be checked if this buffer overflows, because sometimes what people used to try to do is attack was let's overwrite the parameters of the locals, and maybe that can trick this program into doing what I want. So they're basically taking away that opportunity. One thing about canaries, though, is that they're not on all types of buffers. Like let's say you have a buffer of pointers or integers. This canary is not going to be there, and that's typically because you're not going to be asking someone on the internet, oh, give me a bunch of integers. You're going to be asking for characters almost always. Are there any other questions? Yes.
What did you do to determine the layout of the stack and where all these pieces were and be able to get the addresses?
That's an awesome question, because this is where the fun of this project really came into play. So I used several tools. The main one was GDB. So for any aspiring hackers out there, I would suggest you learn GDB really well, because what you can have it do is print out arbitrary sections of the stack. There's this command x/bx, and then you give it an address, and it'll just print out hexadecimal data at each of those stack addresses. So that was very helpful. There's also a command info registers that will show you your registers. So, you have your RBP here and your RSP up here if your buffer is there. And so if you do info registers, then you can get where these are pointing. Now you know where to go on the stack to print out these values. Another very helpful tool was strace. And all that does is trace stack function calls. And so that way that was really helpful to me to say, okay, am I throwing things on the stack in the correct order? Because it's going to show you, it pretty much prints out my exploit as it's happening and says, okay, this is what it's doing on this step, and here it goes, and here it goes. So that was the main tool. There's one more thing. If you're in GDB, you can type info proc mappings, and that will give you a whole printout of your whole address space for this current running program. Yes?
Is the layout of the size and layout of the stack that you're attempting to overflow into, is that necessarily deterministic?
It depends. If you have ASLR on, it's pretty hard to determine what's going to happen here. With ASLR off, it's going to be the same every single time. So, but even with ASLR on, there are some things that are very consistent. So typically what will happen with ASLR is, you have this stack frame, and all that's going to do is put some huge buffer space between your next stack frame. So, this can be, thousands of addresses in between here. And so that way, I've actually tested this. You can just write a for loop, to keep writing memory into your stack. And it'll let you keep going for a really long time before it'll give you a segfault, because it has this huge area in here that, you can write kilobytes of data to it.
But within the stack itself, is that always going to be deterministically laid out?
Yes, pretty much. I think there are some new security features they're trying to make canaries a little bit better. So In fact, there is another canary that usually shows up here. And depending on what you're doing, there might be some sprinkled throughout your stack. But that's one thing though, is that it's pretty easy to figure out where those are. So if someone has access to your source code, they will find security exploits if they are there. Yes.
So you mentioned that you were trying to develop a way with ASLR where you could get it to go. Could you
Yes.
go into either the errors that you were running into or what happened so that you would have a success rate?
Yeah, so I'm still working on this because there's tons of techniques out there that hackers have used over the years to improve their success chances. So, back in the day before these security features were, you pretty much had a 100% success rate if you pulled off your attack correctly knowing these things. Now there's lots of other techniques. There's one called return-oriented programming where you actually just jump around within a program to grab little sections of code that tweak how it runs until you can finally exploit it. There's, as I said, the no-op sled. So what happens with that is when you overwrite this buffer, you put a bunch of what's called a no-op instruction in here so that when you have that return address set, it has a lot of leniency for, I can jump up here and then it's just the no-ops just do nothing. So it's gonna jump up here and do no-ops and then just keep going through it until it finds your shellcode. So it's really about how can I improve my success chances.
Thank you, Scott. Okay, so I would like to invite Dr. DeVore here to hand out awards for the WICS, Women in Computer Science Club.
Yep. All right. Yeah, I just want to recognize this year's WIPS officers. So starting with the president, Melissa Morrell. Thank you. The vice president, Cindy Batres. The treasurer, Kelly Morales. And the secretary, Julie Rosen.
Thank you.
Dr. Watts, Computer Science Club.
And I would like to recognize the officers of the Computer Science Club. Before I do this, I would like you to look at all these people and realize that they have been great contributors to the department, giving us opportunities for a lot of fun, additional education, and if you are not graduating this semester, or next semester, you might, because I think that all the elections have been done for next semester already, you might want to consider doing this and doing your career here. It's a lot of fun. Okay, President Kelsey Rangel. Vice President Nick Nagy. Treasurer Jeremy Swedlow. Secretary David Fisher.
Photo bomb. Jump in.
Last minute jump in.
We truly appreciate the service of the officers of both clubs. Like Dr. Watts said, They truly do add a lot to our department, educationally and socially. Great service. The majority of the faces that I see are on the road to graduation, maybe with the exception of one or two. I'm just simply wanting to emphasize what Dr. Watt said. Please do, like we see some more faces who are going to be around. I want to emphasize to this service. Please do volunteer, great work, and of course it provides kind of segue to my next part, which is my distinction and pleasure to give out the graduation with distinction awards. We, in a way, this semester and every semester, honestly, have a hard time choosing people who graduate with distinction, simply because we have a lot of very good students. And choosing the ones that we feel should have this award is not an easy task. Relies on three different components or three different criteria. One is a GPA of 3 or above. 2 is to have done some service to the department, and that part, really, the service, the definition of service, is quite broad. And I want to emphasize that. Sometimes that is not exactly the most visible component. And third is to have gone beyond the scope of each course and have taken that additional step to put it all together. And one of the advantages and really one of the benefits of the talks that you hear when students give presentations is precisely that. You look at the presentation and you look at it to see what's the depth of this presentation, how far has this person gone. That's not necessarily in number of lines of code they have written. It's just the depth. Anyway, it's my pleasure to hand out these awards. The first one goes to Kai Jansen. Yes. Joji Kubata. Nick Menke. Lowell Olsen. Of course. Chelsea Rangel. Reagan Rickert. May I ask the faculty to join us? And the club officers, one of them is already here.
Do we have room for one?
Wicks, find the spot. Wicks officers and the CS club officers, please.
That's how you do that. Someone said we did. Yeah, we're doing it. No, I tried that last time before Kelly.
Yeah, thank you.
That's how you work. Take the initiative.
Just do a bunch so that way one of them was right.
You can stitch them together.
Yeah.
Photoshop, man, that's what they have that for. Did you volunteer? I think I heard you volunteer.
No. Closed eyes.
Yeah, looks good.
All right, thank you so much. So, the semester is over, the year is over.
Finals, not yet.
Oh, sorry.
Grading.
Grading.
Is it done? We're done?
No, we're not. Not exactly.
Okay, cool.
You don't want to
Everybody's
work to rate it. You're already in a good place. You have the finals to take. You have the finals to grade. And for some of us to make it still, the projects and everything else. Truly, I think this was a wonderful year. I know that much of it is hard work. Hopefully, it's all worthwhile. I want to recognize the faculty for the outstanding job that they do with little resources that we have. It's really amazing. We have about 300 majors, and we have 4.5 tenure track faculty. So just do the math, about 60 to 70 students per tenure track faculty. And of course, when you have so few tenure track faculty, there's much that the faculty have to do to carry the department and the courses. So I want to recognize that, and I truly appreciate all the hard work that the faculty put into it. Thank you. Liz Meyer, who is not here, is truly a fantastic AC. She is just incredibly competent, and we hope that she stays with us for a long time. Our department has been stable for a while because of her, and we really appreciate all the hard work that she does. She's very good at what she does. So even though she's not here, thank you, Liz, for an outstanding job. And Roger Maber, who does not, he has a hard time finding out whether he should be upstairs or downstairs. And when downstairs, which room he should be in and which fire to put out. We really appreciate his work. Yesterday it was, Tuesday, the president and the provost came to our department, kind of took a tour of our department. We showed them around. We told them the really excellent work that gets done in the department, and the students that we have, and the education they get, and the jobs that they get once they graduate. And we showed them the labs, how busy they are, and the challenges that we have. Of course, we have 3 simple challenges. 1, we need more tenure track faculty. That's one of the huge things. 2, we need more space. We don't have enough space. And we still are going to settle for additional space, even if it didn't have windows, which our labs don't have windows. But still more space. Of course, we're working on windows. And then the third item is just the hardware, the systems that we use. We have a whole lot of systems, if you've gone to our server, systems that are quite old. And we could replace them all, like about 10 or 15 of them, with one nice, powerful system and virtualize it and cut out many systems from it. So those are really the 3 large items that are concerns that we have, challenges that we have to run the department. They understand it, and they're working on it, but unfortunately it appears that the number of tenure track faculty searches that we're going to have next year is minimal. Right now, they are talking about 4 for the entire university. So much for the promise that last year, as in the searches that ran this year, next year, and the following year, every year we were supposed to get 15 positions for the entire university, so some of 45. This year we had about 19 searches. Ours failed last year only because we didn't offer enough money. But so that added to the 15, but nonetheless. So this year we actually did have searches, and of course we did hire a new faculty, as you know. But for next year, instead of 15, we have 4 positions right now. This is for the entire university, and the university has more than 4 colleges.
When did that drop from 6?
6 is questionable. 4 is short. My guess is it's going to get increased, but right now it's not very easy. Anyway, I complained enough. To complain to people above me, but then let me complain here.
So go get your PhDs and come back and teach.
Be underpaid in paradise. It's going to be amazing.
The retirement benefits are great, though.
Or wait, are you telling us as alumni we should donate to the school?
No.
Well, there is that
To the
issue.
department.
To the department. Carpenter.
No, it's a CS department. Okay, gotcha.
Make sure that it's very specific.
Yeah, come back
Thank
and
you
work
so
for us.
much. We really appreciate you. We really are proud of our students. It's not always smooth, but we hope that in general your experience is a good experience. And if it's not, we really want to know about it. We want to hear about it. Let us know how we can improve what we do.
Year after year, we hear you get up in the front and talk, and you never get the big round of applause. Hey, you do all the work.
Awfully nice. Thank you so much. Good luck with your projects, with your finals.